Okay, so the thing that we could easily measure if ever there is heat flow is a change in temperature. Okay, so if the system is transferring heat to the surroundings, okay, so this is characterized by a negative Q, we expect that the system will be decreasing in temperature. The surroundings, on the other hand, is expected to increase in temperature. Okay? However, usually the surroundings is so large relative to the system that its change in temperature is considered to be negligible. So more or less, we usually treat the surroundings to be constant temperature despite being a heat sink or a heat source. Okay? So if the surroundings, on the other hand, is transferring heat to the system, okay, so our notation here is positive Q, we expect that the system will be increasing in energy and therefore its temperature will also increase. Okay, so the surroundings, again, we're assuming that it's very, very large, so its temperature change is not going to be as significant as that for the system. Okay, so how do we determine the amount of heat transfer? Okay, so these are the major factors that determine the amount of heat transfer. Okay, so one, if there is a greater temperature change, there's usually a greater amount of heat involved, and the amount of substance and the nature of substance will also matter. Okay, so if we're looking at infinitely small heat transfers, we could combine all these factors and get this equation over here. Okay, so dq, an infinitely small heat transfer, is equal to nc dt, where c is your heat capacity, which is related to the nature of the substance, and N is your amount of substance in terms of moles. Okay, so you could also write this in terms of mass. Okay, so instead of moles, you could express the amount of substance in terms of mass instead. Okay, so you need to express your heat capacity in a different way as well. Okay, so heat capacity, this is the amount of heat required to raise the temperature of a given amount of substance by 1 Kelvin or 1 degree Celsius. Okay, so if we are writing our amount of substance in terms of mass, okay, we'll be using the specific heat capacity. Okay, so the unit is usually joules per gram Kelvin or gram degree Celsius. Okay, so we also see the specific heat capacity in terms of calorie. Okay, so molar heat capacity, this is for 1 mole of a substance, so this corresponds to this particular heat capacity over here. So again, the units is joules per mole Kelvin. Okay, so let's look at the different specific heat capacities of different materials. Okay, so the thing to keep in mind here is if ever we have a low heat capacity, okay, so let's look at different metals. So for metals, we tend to have a relatively low heat capacity over here, less than 1. Okay, so this implies that if you apply a certain amount of heat, this will be manifested in a very large temperature difference. Okay, however, if you have a larger heat capacity, so let's look at this for water over here, 4.184 joules per gram Kelvin. Okay, so that means even if you apply a certain amount of heat, okay, so this won't necessarily result in a very large temperature change. Okay, so that's why liquid water is such a good heat sink or heat source, because even though it is involved in a lot of heat flow, okay, it doesn't necessarily change its temperature drastically. So also note that heat capacity is going to be dependent on the phase of matter. Okay, so we have different heat capacities for ice, for liquid water, and for gaseous water. Okay, and it's also going to depend on temperature. Okay, so here we have water vapor at 100 degrees Celsius and it has a different heat capacity. Okay, so let's look at the dependence of heat capacity on temperature. Okay, so let's look at this graph over here. We have specific heat capacity against temperature. So we can see that there is a temperature dependence. Okay, so it tends to increase with increasing temperature. And then over here we have a divergence of two different types of heat capacities, which we'll talk about a little later. Okay, so keep in mind again that when we were writing heat flow, we're always very careful about writing it in terms of differentials. Okay, so dq is equal to nc dt. Okay, so this heat capacity over here can have a dependence on temperature. Okay, so we could rewrite this as c is equal to some function of temperature. Okay, so we could write it as some constant a plus bt plus ct squared onwards. Okay, so these constants over here, they're going to be unique for each different substance, and they're usually experimentally determined. Okay, so if we're going to be evaluating heat, then we need to take into account this temperature dependence of our heat capacity. Okay, so we write dq is equal to n, so let's replace our heat capacity with this expanded expression here, a plus bt plus ct squared onwards times dt. Okay, so in order to get values for heat, okay, during the entire process, okay, we need to integrate, okay, from the initial to the final states. Okay, so here we're integrating with respect to temperature, so we integrate from the initial temperature to the final temperature. Okay, so upon integrating this inexact differential, we get the absolute value of heat involved in the process. Okay, and then we have to integrate this expression here. Okay, so overall we have n times AT plus b over 2 t squared plus c over 3 t cubed onwards, okay, evaluated from the initial state to the final state. Okay, so just be very careful if ever we're given a temperature dependence of our heat capacity. Okay, so for simplicity, however, sometimes we just assume that the heat capacity is independent in the temperature range of interest. Okay, so temperature range of interest, that means the limits of our integration over here. Okay, so sometimes we just assume that C over here is a constant. Okay, so if ever we're integrating, we integrate from the initial to the final state. Okay, and then we get Q is equal to N. Okay, so instead of integrating C with respect to T, okay, we're saying that it is independent of temperature in the temperature range of interest, so we could just evaluate it as NC delta T. Okay, so this is the simplified form over here. Okay, all right, so let's also look at this special divergence over here. Okay, so we could see that at relatively higher temperatures, suddenly we have two types of heat capacities. Okay, so we have a CV and a CP. Okay, so what is that exactly? Okay, so in certain conditions, okay, so the heat that's involved in the process becomes dependent on the pathway in which that heat was transferred. Okay, so it's going to depend if the process occurs at constant temperature or at constant volume. So at constant volume, we could write the heat involved as QV. Okay, so let's just take the differential. Okay, so dQV, this is going to be equal to N. Okay, so the heat capacity is also going to be at constant volume. So NCV dt. Okay, so we could get an expression for CV. So CV is equal to 1 over N. Okay, so now we're going to get a ratio of these differentials, which gives us a derivative. Okay, so dQ over dt at constant volume. Okay, so we're just writing it in this way to indicate that it's a multivariable derivative, and then this is the variable that is kept constant, okay, our volume, right? So we could also have our heat capacity and our heat at constant pressure. Okay, so we could write dQp is equal to NCP dt. Okay, and then just solving for Cp, we get 1 over N. Okay, so partial of Q with respect to T, okay, at constant pressure. Okay, so this is the more formal definition of CV and Cp. So later on, we'll also look at other ways that we could define CV and Cp and the significance of this divergence over here. Okay, but the thing to note is that this divergence of heat capacity becomes significant only at high temperatures. Okay, so this is usually when the substance is a gas. Okay, so before this is when the substance is a liquid or a solid. Okay, so if we're going to be looking at the different values of Cp and Cv, okay, so for liquids and solids, Cp is pretty much just approximately equal to our Cv. Okay, so for gases, however, this is when the divergence becomes significant. So we could see from our plot over here that Cp is greater than Cv. Okay, so we'll look at the meaning of this exactly a little later on. Okay, so for ideal gases, we could establish an exact relationship between these two values. Okay, so if we get the difference between these two, Cp minus Cv, this is equal to R. Okay, so this relationship over here is going to be very useful for us in our calculations. Okay, so let's differentiate between the molecular nature of work and heat. Okay, so usually we've just been defining work and heat as different ways of energy transfer, but let's look at this molecular interpretation. Okay, so work is a force that causes a net displacement. Okay, so on a molecular basis, okay, so if we are transferring energy via work, okay, so we're applying a force and we're causing a net displacement. Okay, so there is overall an orderly molecular motion that results from the application of work. Okay, so overall we see that there is a net displacement of matter. Okay, so we can easily see this with expansion and compression processes. We could see overall the displacement of our gas, for example. Okay, so in terms of heat, however, okay, so heat is a little bit more abstract. Okay, so we just need to visualize what's happening in our molecules here. Okay, so if ever we're transferring energy via heat, what we're doing here, instead of work, which is orderly molecular motion, we're causing more disorderly molecular motion. Okay, so you could kind of see this as microscopic work. Okay, so if ever we're transferring heat to our system, we're increasing the temperature, so we're increasing the, say, the kinetic energy of our molecules. Okay, so the molecules are going to be colliding with one another. Okay, so they're causing the other molecules to move around. So you could kind of look at that as microscopic work. Okay, but since it's not really happening in any orderly fashion, okay, it's kind of chaotic. Okay, so collisions are going to be random. Okay, so that is what characterizes heat transfer. All right. Okay, so overall, let's just go over the different notations that we have for energy transfer. Okay, so if ever we have energy flowing into the system, this is characterized by a positive Q. And if ever we're having work done on the system, such as a gas compression, okay, so the sign for W is positive. Okay, so these two processes result in an increase in the internal energy of the system. Okay, so if heat is flowing out of the system, or if work is being done by the system, okay, so we have a corresponding negative Q and a negative W. So these processes would lead to a decrease in internal energy. Okay, so overall, in order to calculate the change in internal energy, we need to know these two values here. Okay, so you need to measure the amount of heat that was transferred and the amount of work that was done. Okay, so let's try to calculate this in our next example. Okay, so we have two processes over here. Let's just calculate the change in internal energy of the system during these two processes. Okay, so let's look at for A. Okay, so for A, we have a pressure volume work being done against an external pressure, and we also have an absorption of heat. Okay, so let's write down the first law. Okay, so delta U is equal to Q plus W. So we could expand our work in terms of pressure volume work. So in this case, we have a constant external pressure. So we could just write this as Q minus P delta V. Okay, so for our heat, okay, so we're absorbing heat, so that means the sign of heat is going to be positive. Okay, so positive 1000 joules going into the system. Okay, so minus, okay, the pressure volume work that's being done. Okay, so 1.5 atmospheres and the corresponding volume change. Okay, so this is 6 liters minus 4 liters. Okay, so at this point we just have to be a bit cautious about the units that are involved here. Okay, so we're calculating for a change in internal energy, so we expect this to be in terms of an energy unit. So the most convenient will be the joule. Okay, so our heat is already in terms of joule, but our work is in terms of liter atmosphere. Okay, so somehow we need to convert our liter atmosphere into joules. Okay, so you might be wondering, oh no, I have to convert all of these to SI units and whatnot, but don't worry, we already have a way that we could easily convert between these two units. Okay, so let's recall the values of R. Okay, so R has two possible values that we discussed. Okay, so we could use 0.08206 liters atmosphere per mole Kelvin, or we could write this in terms of the joule expression, so 8.314 joules per mole Kelvin. Okay, so since these two values are equal to one another, okay, so they just have different units, if you divide one value by the other, this is just dividing by a form of 1. Okay, so we could use these values as a basis to convert between the joule and the liter atmosphere. Okay, so in this particular case, we want to convert the liter atmosphere to the joule. So let's multiply this by 8.314 joule per mole Kelvin divided by 0.08206 liter atmosphere per mole Kelvin. Okay, so the liter atmosphere is going to cancel out. Okay, so the mole Kelvin also cancels out, and you're left with joules over here. All right, so we have a joule part over here minus a joule part over here. So if you calculate the delta U, the value that we should get is 696 joules. Okay, so overall we absorbed heat. Okay, and also note that we did an expansion process, right? So we went from a smaller to a larger volume at constant external pressure. So that means we're going to be losing internal energy based on this energy transfer here. Okay, so work was done by the gas. Okay, so let's try to calculate B here. Okay, so for another system, okay, so this time we have a compression, and this time we also have a release of heat. Okay, so delta U, this is equal to Q plus W. Okay, so our work is just, again, pressure volume work. Okay, so Q minus P external delta V. Okay, so our pressure is also constant here. Okay, so our Q, this time we're releasing 64 joules of heat, so that means we have a negative sign here, so negative 64 joules. Minus, okay, so note that we're going to be doing a compression here. Okay, so we expect that our overall work is going to be positive. Okay, so negative 2.50 atmospheres. Okay, so final volume is 5.5 liters. Initial volume was 8.5 liters. Okay, so don't forget to convert between liter atmosphere and joule. So 8.314 joules. Okay, so I'm just going to write it here. I'm going to be omitting the per mole Kelvin since it just cancels out anyway, over 0.08206 liter atmosphere. Okay, so liter atmosphere cancels out. Okay, so we have joule here. Okay, so if we calculate this ends up being 696 joules as well. Okay, so overall for both of these processes, this involved the same change in internal energy. Okay.